Okay, in this video I want to give just a brief introduction to polarity of molecules, and then I have a second video that goes into more detail. So we've previously talked about the fact that bonds can be polar or nonpolar, right? Bonds can be pure covalent or polar covalent. And that's determined by the differences in electronegativity between the two atoms that are bonded. Maybe even more important than whether or not bonds are polar are whether or not the entire molecule is polar. So when we have a polar molecule, it means that one region of the molecule is partially negative and another region of the molecule is partially positive. And whether or not molecules are polar is incredibly important, and it determines a lot of their properties. It influences things like boiling points. So whether or not a molecule is polar determines how that molecule interacts with other molecules. So it influences things like boiling points and solubilities. If I have a molecule with negative and positive regions, it's going to want to stick together with other molecules that have negative and positive regions, and so it's going to be harder to separate those. It's going to be harder to convert them from a liquid to a gas, or when I'm mixing things. And very important phrase that we're going to deal with more in a later chapter is the idea of like dissolves like. And so molecules that are polar tend to like to dissolve or mix with other molecules that are polar. And things that are non-polar, so they don't have these negative and positive ends, they tend to like to mix with other things that are non-polar. Now, we consider whether or not the molecule overall is polar. We have to look at both whether or not it has polar bonds, but then also the molecular geometry, or the shape. And so water and carbon dioxide are two great examples of why the molecular geometry is important. So water is bent or V-shaped, and it has polar bonds. Oxygen is more electronegative than oxygen and hydrogen, and so electron density is pulled away from the hydrogens and towards the oxygen, and so water ends up with a partial negative charge on the oxygen end and a partial positive charge on the hydrogen end, and so the water molecule is polar. Carbon dioxide, as a counterexample, also has polar bonds. Oxygen is significantly more electronegative than carbon, and so the oxygens are pulling electron density away from the carbons, or they're trying to. But the fact that carbon dioxide is linear means that the oxygens are pulling in exactly opposite directions. They have each of the oxygens has the same electronegativity difference with the carbon, so they're pulling equally, and they're pulling in exactly opposite directions. And so if you imagine a tug of war going on for the carbon's electrons, it effectively ends up in a tie because the oxygens cancel each other out due to the symmetry of the molecule. And so even though carbon dioxide has polar bonds, the molecule overall is non-polar. And we'll look at many more examples of this in the next video. Alright, and so in order for a molecule to be polar, we must satisfy two criteria. It must have polar bonds, right? So the electronegativity difference between any two atoms that are actually connected to each other has to be bigger than 0.4. And then the molecule has to be asymmetrical or unsymmetrical. If it's perfectly symmetrical, then those electronegativity differences are just going to cancel out. And so we have to sort of do vector addition in our heads to visualize what these molecules look like. And so we need to be able to draw the Lewis structures. We then need to be able to use VSEPR to determine the molecular geometry to see what the symmetry in the molecule is. And again, polarity is maybe one of the most important concepts in chemistry. It'll keep coming back over and over and over again in a lot of different contexts. And so I have a follow-up video that explores this in more detail.